Well, thank you very much for the invitation. It's a pleasure to be here virtually and to meet all of you. So today I will talk about three papers that I wrote with my collaborator Nick Rod, who's at UC Berkeley, over the past few months and now about a year, on applying methods of bounding theories using means that are agnostic to the details of the ultraviolet completion. So bounding the effective field theory of the standard model in a way that is model independent and that helps us constrain what sort of the space of new physics can be. So as motivation, we're sort of in a unique era of particle physics right now. The Higgs, as we all know, has been discovered, but so far we haven't seen evidence of supersymmetry. And so we might be in a sort of post-naturalness scenario, or a scenario in which we need to rethink the naturalness principle. And this has left model building, of course, wide open. There are the possibilities run the gamut of new physics, hopefully relatively soon, or we could be in the desert scenario. And if we do see new physics, it could come from precision measurement rather than producing new on-shell states. And we might see these hints of new physics in a gamut of possibilities ranging from muon G-2 to Higgs factories, the high luminosity LHC, flavor violation, and others. And so it behooves us to try and understand as best we can the parameter space of the standard model effective field theory. So how do we build a quantum field theory in the space of all effective field theories? Well, we write down a Lagrangian built out of some operators that have some couplings, the Wilson coefficients, and we quantize it. We read off the Feynman rules, compute Feynman diagrams, etc. In this case, my base Lagrangian is the standard model, and I'll be thinking about higher dimension operators, higher mass dimensions, so higher derivatives. And we can ask ourselves, is this process guaranteed to create a consistent EFT, this sort of textbook computation of amplitudes and cross sections? And no, not all couplings are allowed. So certain signs and even certain magnitudes of couplings violate infrared physics principles like unitarity, analyticity, and causality even. And this has been used in really sort of the past few years. There's been an explosion of work on this in bounding all sorts of different theories in papers I've written with collaborators and that other people have written, and it's found rather exotic applications, everything from higher curvature terms, quantum corrections to the Einstein equations, to proving the A theorem in 4 dimensions by Komargatsky and Schwimmer. But despite all this great progress, little has been done until really the past year to apply infrared consistency techniques systematically to the full standard model EFT itself. There have been some prior papers on pieces of the standard model EFT, but not really the full-blown thing until recently. But there are compelling experimental reasons for doing so. In the parameter space of possible higher dimension operator coefficients, here I've sketched here, our experimentalist friends will place bounds that schematically look like this, that are some error bounds around the origin. But generically, IR consistency bounds cut through this parameter space, and every single infrared consistency bound you place rules out an order 1 fraction of the parameter space. So this is a really powerful theoretical prior that we can place, and that not only tells us where to look, but increases the statistical power of experimental bounds. And turned on its head the other way, were we to ever observe a signal of a Wilson coefficient in the forbidden region, that would tell us something even more shocking. It would tell us that some of our axioms of quantum field theory are breaking down in the UV. So it's an important thing to do and a timely thing to do. And in fact, the LHC has already been bounding higher dimension operators in the standard model EFT, but without these theoretical priors in place. So in this talk, I'll be applying, as I said, analyticity and causality bounds to constrain the standard model EFT. In particular, I'll be thinking about 4-point operators, so quartic vertices, And I'll want a number of momenta divisible by 4 initially to apply the standard sort of bounds. And I'm going to consider either all bosonic or all fermionic operators and scatter states of fixed standard model charges for simplicity. So this means that first I'll consider mass dimension 8 operators that go like 1 over the UV scale to the 4th. In the standard model EFT, there are 64 such bosonic operators and 2,763 fermionic operators, for which I'll derive 27 independent bounds on the bosons, if we get time, 25 independent families of bounds on the fermions, and connect these to between LHC searches and other experiments like Neutron EDM, U3E, etc. Furthermore, I'm going to show you how we've developed new kinds of dispersion relation arguments that allow us to use scattering amplitudes to bound dimension 6 operators, which isn't normally possible. So in particular, we're going to look at the 4 Fermi operators, which have coefficients going as 1 over the UV scale squared. In the standard model EFT, there are 1,395 fermionic operators that we'll consider at dimension 6, 23 families of bounds. And again, we'll be able to use this to connect qualitatively different types of experiments in a really interesting way. So first, let's just review how infrared consistency works. So I'm going to first review this with a toy theory, a massless scalar with a shift symmetry as considered by Adams, Arkani, Hamid et al. In their seminal 2006 paper. So here, the first higher dimension operator is d phi to the 4th operator, and we want to bound the Wilson coefficient C. So we can compute the 2 to 2 scattering amplitude, and it goes like Mandelstam S squared plus T squared plus U squared. And we want to consider a forward amplitude, so in state equals out state. So the amplitude goes like S squared times the Wilson coefficient. So you should be thinking, okay, if you're hearing the words forward amplitude, that should be put you in mind of the optical theorem, and indeed that's what we'll be using to place positivity bounds. So what we're going to do is we're going to go to complex momentum space, and in complex momentum space, amplitudes have beautiful analytic properties, and this is just the Fourier transform of locality. So we're going to extract the Wilson coefficient by just doing this nice contour around the origin, and then use the analytic properties of the amplitude to deform the contour. So the laws of physics care about a finite number of derivatives. That means in momentum space, they should be a Taylor series in momenta, and in terms of amplitudes, they should be analytic almost everywhere in the plane, except for branch cuts or poles along the real s-axis, which are associated with on-shell production. So the boundary term at infinity vanishes as long as the amplitude satisfies fairly pedestrian properties. It has to fall off at infinity more quickly, or not diverge at infinity as quickly as it does in the IR, which any UV completion will do. By crossing symmetry, here for this simple scalar theory, crossing symmetry, swapping particles 1 and 3 just amounts to the amplitude in the forward limit being even under S, because S and U swap. And I can relate the imaginary part of the amplitude to the discontinuity via the Schwartz reflection principle, just that if I have an analytic complex function, and if I conjugate its argument, that's the same as conjugating the entire function. So I've related the Wilson coefficient to an integral over the imaginary part of an amplitude. And now we invoke the optical theorem, which is a consequence of quantum mechanical unitarity, which just tells us that the imaginary part of the forward amplitude equals the cross-section up to some power of energy. So what we get is the Wilson coefficient is the integral over a cross-section in the UV. And cross-sections are areas. They're positive. They're just the norm squareds of amplitudes. So C is positive. Great. So we're going to use this and apply the same idea to bound fermionic operators in the standard model first. So we want all 4-point fermionic operators that have 2 extra derivatives, so that we're at dimension 8. And the counting can be found in this paper by Henning et al., but not the operators themselves, but we went and enumerated them. So we have to take as our ingredients the standard model fermions. So we have the left-handed fermions, the quark and lepton, multiplets and right-handed fermions, E, U, and D. And all of these are indexed by a generation index, a flavor index that runs over 1 up to NF, where in the standard model, NF is 3. So these define the flavor quantum numbers like lepton flavor number, strong isospin, charm, etc. And what we'll find is that the bounds give us interesting structures among the flavor indices. That is, the Wilson coefficients for these operators will be tensors in the space of flavor. All right. So to construct the minimal basis, we had to mod out by a bunch of identities, Fiertz and Schouten, SUN identities, equations of motion, etc. But doing so, we get the following operators. So they come in a few different classes. There are self-hermitian, self-quartic. So these are d psi bar psi. So here I'm defining all these currents. J mu is psi bar gamma mu psi, and then there are various versions that are decorated with SU2 and SU3 generators. But the basic form of these operators is d psi bar psi, d psi bar psi. And so these are the self-hermitian self-quartics. And we have our Wilson coefficient tensor C MNPQ that we're going to bound. Similarly, there are self-hermitian cross-quartics. So for example, d u bar u, d q bar q, for example. And finally, there's another type of cross-quartic that isn't d current. It instead looks more like the contraction of two stress tensors into each other. So if we define these k mu nu tensors that look like kind of half of the Dirac stress tensor, we can contract these into each other to generate some independent cross-quartics. So we will bound these Wilson coefficients A, B, and C. All right, we can ignore for now lower dimension operators. There aren't any dimension 5 and dimension 7 purely fermionic operators that we have to think about. Moreover, there could be dimension 6 operators, but in order to generate S squared amplitudes, we would have to take a loop, and in a sufficiently coupled UV completion, we can ignore these at leading order. So at dimension 8, here's what we get. So we're first going to scatter right-handed leptons for simplicity, because these have less of the structure of the other multiplets. So I'll take psi1 to be an E bar, psi2 to be an E, and here alpha m and beta m are wave function coefficients. So rather than just scatter an electron, a muon, or a tau, what I'm doing is I'm scattering some arbitrary superposition of these different states. And so these are my in states and these are my out states. Similarly, they have wave function coefficients gamma and delta. And I'm requiring forward scattering. So that means I have to set alpha equal to delta star, beta equal to gamma star. And I compute the forward amplitude. And what I get is the Wilson coefficient tensor C MNPQ contracted into a quartic form among the alphas and betas times S squared. And we expected S squared just by power counting. So we know by the argument I showed you with the d phi to the 4 theory that unitarity and analyticity will require that the S squared coefficient of the forward amplitude be positive. And indeed, requiring that for this operator requires this full set of bounds. CMNPQ dotted into alpha, beta, beta star, alpha star has to be positive for all complex vectors, alpha and beta. So please stop me at any time if you have questions. But that's the basic form of the fermionic bounds that we get. And so we can think about these before we move on. It's useful to develop some formalism to think about what these bounds are really telling us. So we can think of the outer products of alpha and beta as matrices. And they're automatically idempotent, permission, and with trace 1. So they really behave as density matrices for a pure state on a Hilbert space of dimension NF, where alpha star is just the Schmidt decomposition for this density matrix. We define C alpha beta as our Wilson coefficient tensor CMNPQ dotted into these two density matrices. The positivity bound is just that the C alpha betas are positive for arbitrary density matrices. So let's go through an example. And this is sort of reminiscent of Nima Arkani Hamed's EFT hedron work in terms of carving out the space of the allowed EFTs. So we've called this somewhat humorously the flavohedron that we're carving out. But in a simple theory of two flavors, where we have CP conservation so that all the Wilson coefficients are real, and let's further assume that C1111, 2222, and 1221 are all equal, and similarly impose all these other constraints, then our bound just becomes this set of inequalities. And so this is something we can plot. And we can see that it's non-trivial. It's not just a simple positivity bound. It actually bounds magnitudes of Wilson coefficients. So these are cuts through this three-dimensional space of couplings, or I can visualize it like this. So it's this shape that it makes in the space of ratios of Wilson coefficients. So, and something to note about this is that X1 violates flavor by 1 unit, X2 violates flavor by 2 units. And what you find, and C doesn't violate flavor at all. So what you find is that the flavor violating couplings divided, the size of the flavor violating couplings divided by the size of the flavor conserving couplings is upper bounded. You can't arbitrarily badly violate flavor symmetry. And we'll see that come back in force later. So we can add in SU2 charge. So let's add in the L to the 4 operators, of which there are 2 types, one decorated with the generators. And so now our wave function coefficients describe superpositions not only of generation, but also superpositions of different SU2 charges. So we have to mod over not only the direction in flavor space, but also direction in SU2 left. So we do that. We write down the bounds that we get for arbitrary wave function coefficients, as shown here. And now I can, for simplicity, well, since each operator is an SU2 singlet, without loss of generality, I can rotate the alpha to be in the one direction and then let beta be some arbitrary other vector. So now I just have to mod over a single angle. Yeah.
Excuse me. What is this SU2? Is it rotation or SU2 left?
No, this is sorry. This is SU2 left of the L.
Oh, okay.
So here, yeah, this is the left-handed lepton multiplet. Good. Right. So I'm just modding over isospin. So my cosine theta describes the angle between the SU2 charge of the alpha and the beta. So I require this to be true for all theta. And so this is the necessary and sufficient set of bounds here. We get two different bounds on linear sums of Wilson coefficients. And a similar thing happens with the quark bounds. Again, we can mod over the SU2 and SU3 charges, and we get various families of bounds on the U's, the D's, and the Q operators. Now, the cross-quartic story proceeds in essentially an analogous way. We compute scattering via the cross-quartic operators I enumerated, and we get lots and lots of families of bounds. And they're all of the same form, that you have some 4-index tensor of Wilson coefficients dotted into 2 density matrices, and you require that it be positive for arbitrary density matrices. Now, some of our operators conserve flavor, while others are flavor violating. So for example, this operator here, you can see conserves flavor because you have a 1 bar and a 1, and a 3 bar and a 3. And similarly, this one conserves flavor interacting an electron with a muon. But this operator here, 1 bar 2, 3 bar 1, violates both muon and tau flavor quantum numbers. Now, what our bounds imply is that various flavor conserving coefficients are positive. So for example, C1111 or 1221 is positive. And these correspond to diagonal density matrices, rho alpha and rho beta. But we could consider more general density matrices. And what we'll find is magnitude constraints on the flavor violating operators. So the flavor violating operators correspond to the off diagonal elements. So concretely, suppose I scatter with my particle 1 state is just an electron, and my particle 2 state is an arbitrary superposition of muon and tau. And I marginalize over all possible superpositions, and I get a new quartic bound. That's C1221 1 times C1331, upper bounds the magnitude squared of C1231. So this would be an operator that would violate the flavor quantum number of the muon and the tau. It would lead to muon tau conversion assisted by an electron. So what we find is that flavor violating couplings are forbidden by unitarity from being too large. They're always upper bounded by their flavor conserving cousins, the Wilson coefficients of their flavor conserving analogs. And this is sort of surprising and really kind of qualitatively different than a lot of the previous sorts of positivity bounds that were seen in the literature, which were normally just statements about positivity of individual operators or superposition or sums of individual operators. So not only is this true for flavor, but one can also show that the only possible CP violating, that is imaginary coupling for fermion operators, are also flavor violating. So the flavor bound also constrains CP violation. And this in fact generalizes to any U1 symmetry. So having derived this big set of positivity bounds, what we should do is sanity check it by looking at some well-defined UV completions that we trust and making sure that our bounds are obeyed by the Wilson coefficients that you generate from those UV completions. So in particular, suppose we have some collection of complex 2-Lorentz index standard model singlet fields, phi, mu, nu, mn. So some massive spin 2s that will couple to dj. And if we integrate these out, we indeed get Wilson coefficients that are manifestly positive. So our bounds are satisfied. This is inspired by a particularly known, well-defined UV completion, a Kaluza-Klein graviton, which couples to, and we can compute the Wilson coefficient tensor CMNPQ, and it's given here. And indeed, contracting this into arbitrary alphas and betas gives us a manifestly positive object. So our bounds are again satisfied. So what we should look next at are phenomenological consequences for these bounds on dimension 8 fermionic operators. So precision experiments are currently searching for flavor violation. And what our bounds allow us to do is to link predictions for qualitatively different types of experiments. For example, linking low energy precision measurements, flavor violation measurements, and colliders, which could search for the flavor conserving analogs. So for example, in muon to electron conversion, mu goes to 3e's. The mu to 3e experiment, if they find non-zero branching fraction via, for example, the C1112 operator, our bound implies non-zero C1111 and C2112, which could be tested at colliders in the dilepton distribution. Now, of course, there are dimension 6 analogs of all of our operators, which I'll get to next. By power counting, dimension 8 operators are suppressed relative to the dimension 6 operators by the square of the IR scale at which you're doing the measurement to the UV scale at which the operators are generated. Now for muon decay, m mu is small, it's just the muon mass. So how can we distinguish this from dimension 8? Well, one thing we can do is use colliders, which allows us to crank up lambda IR to order root S. Another way to distinguish dimension 6 from 8 is differences in the higher angular momentum modes in the distribution that they create, or differences in the high PT tail. Not only this, but the lambda IR over lambda UV squared scaling, mass scale can be more important than a tighter branching ratio. So even though, for example, mu to 3e is more tightly constrained than tau to 3e, the fact that m tau over m mu to the 4th is already of order 100,000 means that we might actually have better luck in phenomenologically testing our dimension 8 bounds by searching among tau processes. And a similar statement holds for any interactions involving the top. So there are, of course, other probes that I could talk about, but I should note that dimension 8 operators are particularly well motivated from a UV perspective, you know, the KK graviton, but also models of fermion compositeness and leptoquarks. Also found, interestingly, are orthogonal to the MFV hypothesis. We neither forbid nor mandate MFV. Though there was an interesting paper a week or two ago by a German group looking at how our bounds can intersect with MFV. So what I want to talk about now is actually to go to lower mass dimension, so an operator that is more both in the technical sense and in the phenomenological sense, and think about dimension 8, so or dimension 6. Normally, traditional dispersion relations require bounding operators with the 4 powers of momenta, so mass dimension or above. But the standard model EFT, as we know, starts at lower mass dimension. There's the Weinberg operator at dimension 5, but really all the interesting action starts at dimension 6, where the basis is enumerated in the literature, most famously in the so-called Warsaw basis by these authors. So it would be nice if we could bound dimension 6 operators using analyticity. Now the 4 fermion operators, in particular, have amplitudes that go like momentum squared, meaning they go like Mandelstam ST or U. But the optical theorem applies in the forward limit. So when t goes to 0, that would mean the amplitude would either vanish or would flip sign under crossing symmetry when we send s to minus s. And this obstructs a straightforward application of our positivity bounds. So for concreteness, consider the 4e operator, the right-handed electron operator. So again, we'll scatter an arbitrary superposition of flavors, and we'll choose our superpositions to correspond to forward scattering. And if we're scattering opposite helicity states, which for reasons it'll become clear is what we want to do, we get the following amplitude. So here I'm using spinor helicity notation. So for the forward amplitude, when t goes to 0, indeed, the amplitude goes like s. And so I could extract the proportional to s part of the amplitude using a contour integral. So I, again, do a contour around the origin. Here I divide by s squared rather than s cubed. And using analyticity, this turns into the imaginary part of the forward amplitude, evaluated integrated over the plus s axis, minus the imaginary part of the, and how that comes is by integrating over the minus s axis, swapping s for minus s under crossing symmetry, and so turning it to a positive s integral over a cross process, so a process with complex conjugated quantum numbers on one of the particles. The s squared rather than the s cubed in the denominator is what resulted in this sign flip. And under, as I said, under crossing in the second guy, all the quantum numbers are complex conjugated. Now there's also this boundary term at infinity, but we'll drop that because that vanishes if the amplitude diverges more slowly than p squared at large momentum. That is, the UV is better than the IR. Fairly mild assumption. Now, since the imaginary part of the forward amplitude is positive by unitarity, this integrand has indefinite sign. So one could still use a dispersion relation to write some rule, like, as some authors have done, under assumptions about the UV theory. But we will better. So what we can do instead is abandon the forward limit temporarily. So using properties of partial waves, not only is the imaginary part of the amplitude in the forward limit positive, but also all of its t derivatives are positive. And this is just a feature of the Legendre polynomials. All the Legendre polynomials through 1 when cosine theta equals 1, but they also all have positive slopes, and all of their derivatives are positive. So let's consider a contour integral at non-zero t. So we're sending s to 0 because we're doing the contour around the origin, and we're extracting the proportional to, well, actually we're just extracting the value of the amplitude itself. And we deform the contour to integrals over the positive and negative real s-axis. plus a boundary term at infinity. And again, this boundary term at infinity will go away under relatively mild assumptions about the behavior of large momentum. So in particular, what we want is that the limit as t goes to of the t derivative of this term to vanish. So we'll drop that. And taking sides, we again find the sign ambiguity. And here the sign ambiguity is coming from the fact that the derivative can not only hit the amplitude, but it can also hit the t in the denominator. So interesting side note, this precise obstacle of the sign ambiguity here is what stymies Elvang and friends attempt to prove the A theorem in 6 space-time dimensions. But we can combine these two observations into something useful. So we'll add these two sum rule dispersion relations. We still have an indefinite sign, but now what we're going to use is partial wave expansion to resolve this. So let's try and better understand this object. We'll expand in partial waves into final states of total fixed angular momentum. So for A alpha bar beta, since we're scattering opposite these states, A alpha bar beta means we're scattering same helicity states. The total initial angular momentum is 0, and the partial wave expansion is just done in the usual way as for scalars in terms of Legendre polynomials. But for our original amplitude, the total initial angular momentum is 1, and we're scattering opposite helicity states. So the S wave doesn't contribute to the expansion, just in the same sense that there's no monopole radiation for a photon. There's no S wave when you start off with unit total angular momentum. In particular, the partial wave expansion is not done using Legendres if you want to expand into states of fixed momentum. Instead, what you need to do is expand using the Jacob-Wick expansion, using the Wigner small d matrices instead of Legendres, and they're given in general. But for us, they can be written in terms of Jacobi polynomials, these p's, and I can difference. So here, the line are the Legendres, and dashed line are the Wigner small d matrices for spin 1. And you can see when cosine theta approaches 1, they become fairly similar, especially for large spin. But for backward spring, they are markedly different. And the slight difference between these will make all the difference. It will allow us to place a positivity bound. So taking our dispersion relation and expanding every expression here in partial waves and rearranging, we find that we can rearrange it into an object that is manifestly positive. Or here, the imaginary parts of the partial waves are by definition positive by unitarity. Great. So now we're really in business. We've broken the dimension 6 barrier, and we can place bounds on the 4 Fermi operators in the standard model EFT. Any questions before I move on? Okay, great. So we have this new positivity bound, and we've really only relied on 2 assumptions. One is that the UV physics has to be Lorentz invariant, unitary, and local. And we require that in the deep UV, the amplitudes diverge more weakly with large momentum than in the IR EFT, in the sense that I made clear earlier. All right, a couple caveats. In the standard model, of course, the exchange of a massless photon in Mahler and Baba scattering contributes with a T-channel singularity. It's physical, it's just the Fourier transform of the Coulomb potential. But we can remove it. We can either IR regulate to give a small non-zero T, essentially an IR mass, so that the singular terms give large but equal contributions on the contours in the standard model around the origin and at infinity. There are no bulk in the pure standard model amplitudes, so these extra residues can just be simply subtracted on both sides with impunity, as Gu and Wang showed. Alternatively, we could study a truncation of the standard model without bosons. But in either case, we don't have to worry about the pure standard model contribution to these dispersion relations. All right, so having said all that, let's see what kind of bounds we get among the dimension 6 operators. So applying our bound to the E4, e to the 4 operator, we get, again, a bound that looks qualitatively similar to what we found at dimension 8. And in fact, in the case of a single 4 Fermi operator, this agrees with the bound predicted by Adams, Jenkins, and O'Connell, which was derived, however, using much stronger assumptions. Now, let's add in isospin. For the L to the 4 operator, there are SU2 left C's contracted within each bilinear. So we get a more complex structure in the amplitude. And once we marginalize over the SU2 vector space, we obtain 2 different bounds, similarly to before, though with slightly different arrangements of the alpha and beta vectors. So if I define Wilson coefficients B plus minus as B MNPQ plus or minus the swapped version, B MQPN, what I get is that these 2 objects have to be positive, where again, I've defined B alpha beta similarly to before, contracting with alpha and beta bilinears. So now we're ready to apply our bounds to the full dimension standard model EFT. We have the following operators. We have and cross-quartics. And we get the following families of bounds, the promised 23 families of fermionic bounds that I mentioned earlier. And this is the first time that model-independent bounds have been derived for the leading matter deviations from the standard model. These are the leading deviations from the standard model among the matter fields, among the fermions, purely using the analytic structure of the scattering amplitudes themselves. So analyticity and unitarity and mild assumptions about the UV. So this is profoundly model independent and a really cool connection between high-minded concepts in formal theory and something that is immediately useful to phenomenology. So again, we need to test. So we're going to test by writing down a bunch of UV completions and making sure that our bounds all obey them. So a nice UV completion is a one-loop completion of the L to the 4 operator with a massive Yukawa. So here I have a massive scalar phi, some family chi A of massive fermions coupling with a Yukawa interaction. And if I do the diagram and integrate out the massive states, I get something that's manifestly positive times some function of the mass ratio of chi. Here this function is this beautiful function here. It's invariant under inverting the mass ratio, but importantly manifestly positive. So contracting BQ with arbitrary alpha and beta vectors, we get positive definite tensors as required. So another completion, simpler one, is just a tree level completion with a massive Higgs. So massive scalar coupling to E bar and L. And so one of our cross Wilson coefficients, and again, are satisfied. Similarly, with a instead of a case, color by fundamental Higgs again satisfies our bounds. So what about massive vectors? So in contrast, we could have coupled a massive vector with fundamental mass to the fermion bilinear. So A mu coupling to L bar gamma mu L. And if I integrate out the vector field, I would find Wilson coefficients that don't necessarily obey our bounds. So what's going on here? Well, this is not surprising because a massive vector has additional powers of momentum in its propagator. So here's the propagator for a massive vector field, and there, as you see, are additional powers of momentum. And what this means is that the amplitude in this theory will still scale like momentum squared in the UV. The pole affinity. This is not actually a UV completion because the amplitude scales and diverges in the UV back as it does in IR. So it's not a counterexample, but it's not UV complete. So we can look at phenomenological consequences at dimension 6. So as at dimension 8, flavor violating dimension 6 operators are upper bounded by their flavor conserving counterparts. So for example, if I choose to scatter an electron against an arbitrary superposition of a muon and tau, I find that similarly that CP and flavor conserving terms are positive, and various CP and flavor violating terms are upper bounded by products of their CP even cousins. Great. So prospects for detection, let me write the flavor violating scale as lambda tilde, the flavor conserving scale as lambda. And our bounds imply that lambda has to be less than lambda tilde. So for mu to 3e, we're the mu to 3e experiment to find muon conversion, flavor violating muon conversion in their targeted branching ratio range caused by a dimension 6 operator. This would correspond to lambda tilde in the 80 to 800 TeV range. But and that's rather outside what we expect near-term colliders. But we can pay. The current PDG bounds on tau decay correspond to lambda much more modest of only 70 eV. And the Bell 2 at super K EKEB aims to improve branching fraction to 10 to the minus 10, so lambda tilde of around 25 TeV. Now, this is nice because the LHC bounds on the flavor and CP conserving terms analogous to this set lambda to be at least 1 to 2 TeV. So these are getting pretty close. This means if there were near-term detection flavor violation in tau decay at Bell 2, that would guarantee the near-term detection of flavor-conserving new physics at colliders in the 10 TeV range. So a guaranteeing of new physics at colliders is something pretty rare these days, and it's exciting that, you know, were Bell 2 to see something, we would be able to make that sort of prediction just as a consequence of unitary and wild assumptions about the UV behavior of amplitudes. So in the last, yes.
One question before you go to the next
Please.
slide. In this example that you gave from mu to 3a conversion, at this level of the 6-dimensional operators, do you have a correlation between the operators entering there and the operators mediating mu to e gamma, for example, or tau to mu e gamma?
So let's see. Well, these dimension 6 operators that we've among the fermions give you tau to for example, tau to mu gamma. You could take one of the operators that, you know, a tau, a mu, and 2 e's, close up the loop of e's and radiate a gamma, for example. We haven't directly considered you know, single insertions of operators that involve both bosons and fermions, but certainly you can loops and attach gammas. I don't know if that, I don't know the full extent of whether LHC observables have been mapped to all of these dimension 6 operators in that way, but that's certainly something that could be done.
Yeah, okay, thank you. I asked because, you know, in supersymmetric theories, they are correlated, so
right.
you can bounce from one or the other.
Oh, good. Yeah. No, that's interesting. No, that's not something we've thought about.
So,
thanks.
So let me ask a related question.
Okay.
For mu to E gamma, there will be a 3-level dimension 6 operator involving so F mu times Higgs and L bar sigma mu E, right?
Let me see. L bar sigma mu E is yes, yeah, yep. That's dimension 6, right?
And do you have such as any bound on this kind of operators or not?
So we have not yet placed one, but it would be possible to bound that kind of operator. But it's the sort of bound you would get. What you'd have to do to bound that, you'd have to scatter something that's a superposition of different kinds of standard fields. So
Right,
it's like, for example, you can formally at the level of the S matrix, you can scatter something that's like a superposition of a Higgs and a photon, right? And and you would, doing so, you would turn on that operator, and it would show up in a bound, be bounded from above by, you know, products of operators containing just photons, or just Higgses instead of a superposition. That's my conjecture. That would be really similar to what we've been finding with superpositions of flavor, but that's not an analysis we've done. And in that case, it would be complicated somewhat by the fact that, well, you wouldn't be able to apply our nice Jacob-Wick expansion in the same way, because, you know, that would, because to turn on that operator, you'd actually have to be scattering superpositions of states of different spin, which would be more problematic for the partial wave expansion.
I see.
So yeah, that would require a separate dedicated.
Thank you.
Yep. Okay, so in the last few minutes, I'll tell you briefly how the story goes for. So we want all the 4-point operators among bosons that have 4 derivatives and their field strengths. So our ingredients are the mu, W mu, and G mu fields of the standard model, along with the Higgs. We again modify all the different symmetries to get operators, and here's the basis. So there are self-quartics, cross-quartics, Higgs self-quartics, Higgs and field strength cross-quartics. But you don't have to remember all the operators. This is just to give you a sense of the size of the problem. There are various reasons analogous to the dimension 8 story with the fermions why I can ignore lower dimension operators. Probably don't have time to go through that, but I'll send you the slides if you're interested. But I'll briefly state what we how we found the bosons. So in addition to analyticity, we can also tell a nice causality story that's much cleaner with the bosons. So here's the equation of motion for our nice d phi to the 4 example. And I expanded around the condensate background, so where d mu phi is a constant. It's kind of like a scalar version of a constant electric field. And expand our perturbation in plane waves. I can compute of the propagation of a perturbation. So it's sort of like taking a 4-point amplitude and pinning 2 of the legs to the classical. And if C, this C Wilson coefficient were negative, then and you can engineer a causal paradox by taking 2 bubbles of condensate and sending signals back and forth between them, and they arrive before they left. So you can use that similarly to analyticity to bound these bosonic operators. So let's start with general SUN f to the 4th operator. And to 0th order in the Wilson coefficients, we can write down a solution of the Engel's equation of motion, where we have some constant vector in color space and arbitrary 4-vector polarization and some coordinate W. We can write plane and compute speed. C are just color-weighted combinations of various Wilson coefficients. So this becomes more clear if I break my Lorentz invariance and write down explicit coordinates, which I've done here. And we get a square. And this should sort of remind you of what we were finding among favor violating operated fermions. So if we mod over all sides this angle between polarizations, we get a completing squares type bound. We get positivity of 2 CP even Wilson coefficients and an upper bound on the CP breaking Wilson coefficient. And we could third condition, had we just bounded fixed, fixed linear polarizations. We had to mod over all different linear polarizations. So in addition to finding this set of bounds from causality, the exact same set of bounds also comes about just from analyticity story, so bounding the s squared coefficient of the amplitude. So for the gluon operator, we get several families of bounds, particularly for SU2 and for U1. And the cross-quartics, we get again these families of bounds positivity among CP even terms, upper boundedness for the CP violating Wilson coefficients. And the Higgs cross-quartics, again, these are all CP even, so we get a set of bounds on the Higgs where we've modded over all possible superpositions of the 4 real components of the Higgs doublet. And similarly for the cross-quartics. So we again sanity check this by kind of throwing the book at it in terms of UV completions. So for the Higgses, we can write down some nice tree level UV completions. So here, for example, I've considered integrating out, coupling to HDH, integrating out a singlet or a bifundamental or a massive spin 2 or a triplet, and they all lie in the cone of operators automatically satisfying our bounds. Similarly, for one loop completions of the gauge operators, we can look at a huge class of UV completions. So essentially, the most general possible generalization of the Euler-Heisenberg Lagrangian. So in QE, we integrate out the electron at one loop in f to the 4th term. Well, here we're going to integrate out an arbitrary representation of the standard model gauge. So some massive state charged under an arbitrary representation of SU3 color times SU2 left times 1 hypercharge. And in this beautiful paper by Fermion, Smith, and Tuati, all of the Wilson coefficients have been computed. And so the relevant set of bounds turns into just, and indeed, all of these are automatically satisfied because all these group theoretic objects are all non-negative by definition. So we notice a pattern in the standard model EFT positivity bounds. They come in 2 distinct forms. Positivity, as I said, for CP conserving terms, and a completing the squares type bound for the CP violating term. So you can visualize this as the allowed region being some round cone in parameter space. And we can sort of understand what's happening with this by trying to generate these coefficients. So at tree level, suppose I integrate them by integrating in a massive dilaton that mixes with an axion. So here I have some mass mixing term between the dilaton and axion. And I generate the b to the 4th operators in precisely this completing the squared form. And this completing the squared form was guaranteed to exist by virtue of the particular pattern of Wilson coefficients that's mandated by unitarity, analyticity, and causality that we proved. So that's sort of fundamentally why this pattern keeps occurring over and over. So again, there are interesting phenomenological consequences among the bosons. So previously, the focus on experimental signals of dimension operators has really focused on the electroweak sector in anomalous quartic boson couplings. So these induce corrections to the standard model couplings like W to the 4th, or induce non-standard model couplings like Z to the 4th. And they can be probed in channels like QQ goes to QQ plus WW or ZZ. And as I said, they can be distinguished from dimension 6 operators since they generate triple gauge boson couplings that are heavily constrained by LEP and by LHC data. So there's a traditional set of operators that are used in studies of AQGCs, as seen in these papers. Type operators of the form DH to the 4th, 7 mixed M type operators, and 8 tensor type operators. But our set of CP even operators has an additional few operators, one additional M type and two additional. And what we've actually found is that literally missing some of the operators from the basis. The phenomenology papers were actually working with an incomplete basis that we did in the literature. Now, interestingly, the LHC has already placed constraint on AGCs. So the ellipse here is MS 95% confidence level in the space of the scalar type operators. And here I've that with the set of forbidden and allowed regions implied by our bounds. You see it really have. Another space here, this is for two of the tensor type operators that can be probed using LHC data, but for which the analysis has not yet been done. Our bounds rule out about 3/4 of the space. Sort of traditional parameterization. So IR consistency bounds can not only sharpen our extant experimental bounds, but they can tell us new places to look. And as in the case of the fermions, where I could connect precision measurement like mu3e to collider bounds, in the case of bosons, we can connect neutron EDM measurements to colliders. So the neutron electric dipole moment famously would violate CP. It's the strong CP problem. And the dimension 6 G tilde operator can generate a neutron EDM. But depending on the details of the model, it's possible that dimension 8 operators could provide the dominant contribution to the neutron EDM. And if that's the case, if the operator is this G³ G tilde operator that occurs at dimension 8, we can estimate the neutron EDM from dimensional analysis. And what we find is that it goes like the Wilson coefficient in units of TeV times 10 to the minus 28 e centimeters. And current experimental bounds require that the neutron EDM is at most 10 to the minus 26 e centimeters. So the scale of M that's being probed if the neutron EDM is generated at dimension 8 is already of order hundreds of GeV. So the discovery of a non-zero neutron EDM from dimension 8, if that happens in the near future, would lead directly to IR consistency predictions for CP even operators that would be observable at the LHC, because they would be of order the TeV scale if it's discovered in the next order of magnitude or two. So that's really exciting, a connection between, yet another connection that we found, that analyticity and unitarity demand a connection between any symmetry violation that's seen in low energy precision experiments and something that we might detect in the near future at the LHC or a future collider. So there are a lot of interesting avenues for future work. Again, finding more connections between CP even and odd measurements, superpositions of standard model representations, baryon and lepton violating operators, which we haven't yet considered. We also want to derive standard model EFT bounds for operators that contain both fermions and bosons, which I haven't talked about yet. It would be nice to apply our techniques to other EFTs, connect with the string swampland program, and more generally move beyond the forward limit using beyond positivity techniques, the EFT-hedron, etc. But the takeaway, I think, is that connecting the IR consistency program that I've outlined here with the standard model EFT and accessible experimental signals gives us a really amazing new bridge between formal theory and phenomenology. We're connecting physics at different energy scales, and we're offering both a test of fundamental axioms of QFT up to high energies and a means to sharpen our search for new physics. So it's really an exciting time to be doing particle physics. And with that, I'll take any more questions you have. Thanks.
Thank you very much. So, question or comment?
I have some questions.
Please.
So hi, and thank you for the talk. And just before the question, just out of curiosity, we have here our journal club, and I had chosen your most recent paper to talk.
Oh, great.
And yeah, so now it won't be necessary. So thank you for that. we'll probably just be hanging out, you know, having lunch, and so that's good.
Okay.
But the
right.
reason that the reason that I had chosen your paper was that most of the works about using positivity bounds and so on, they are applied for dimension 8 operators.
Right.
Like for instance, studying neutral triple gauge couplings and so on. And I don't know if I'm wrong, but I think even the paper by Ricardo Ratazzi in 2006 or so, they also studied applying for considering like dimension 8 operators. And then I had this paradigm that positivity bounds would apply only at this level and further. So,
right.
And your paper shows the opposite, shows that it's actually possible to apply to dimension 6. So the question is, what did they miss by thinking that,
Yeah, no, that's an excellent question. It's not really that they missed something, it's that most work previously has involved just thinking about bosons. Most work on positivity bounds, you know, in the twice scalar theory, for example, that I gave. And really, to apply the bounds at dimension 6, spin was key. That's actually why we titled our paper "Signs, Spin, and SMEFT." So the reason that spin was key was because of the crucial differences between the partial wave expansions appropriate to a scalar versus spinning states. So I'm just trying to find the slide where I talked about that. So yeah, so here, right. So if you're doing partial expansions for a scalar, you use the polynomial. But if you're doing the expansion for scattering a spin plus 1/2 off of a spin minus 1, you don't expand using Legendre's. You expand using the Wigner small d matrices here. And these are orthogonal polynomials that are like the Legendre's, but not quite the same in their numerical properties. And what it means is that, you know, if you try to bound a dimension 6 operator, you know, at first you would get something that looks like this. You would get a dispersion relation with opposite signs in it, and this is the fundamental obstacle to applying positivity bounds at dimension 6, because you always get these opposite signs. And normally this is sort of when people give up. You see opposite signs, and you know that this is positive and that's positive, and you're done. But even though they're opposite signs, nonetheless their sum is still, the residue is still positive, just as a result of the detailed properties of the Jacobi polynomials that appear in the Jacob-Wick expansion. So when we took that dispersion relation that has opposite signs and rearranged it using partial waves, we found that it could be arranged into a form that's manifestly positive. And that was only because we were considering spinning particles. So spin and taking t derivatives were really the magic ingredients here.
So hence the title of your paper is Sign or Spin and SMEFT. Right?
Yep.
Yeah. So yeah, I was wondering about the bounds on bosonic operators at dimension 6 that you mentioned in your talk. But maybe I missed, I don't know. But do you have like some?
Oh, we don't have any
result, like, yeah.
We don't have any bosonic bounds yet.
By that you said, right? Yet.
Yeah, the bosonic bound. Yeah. So and you can sort of see why. In this formula here, so here J starts, the sum in J starts at 1 because I'm scattering plus 1 and minus 1/2 spin. Yeah. Scattering scalars, J would start at 0, and indeed there would be a negative contribution coming from the spin zero scalar, the S wave current in the. So in order to 6 operators among scalars, so like H squared box H squared, for example, one would have to invoke additional whether the UV states are themselves scalars or are spinful. But subject to those additional assumptions, I have some rules. Yeah.
Okay. But what about, for instance, operators contributing to electric precision observables, like those standard operators like plate correction and so on? Like, there would be any bound? But I mean, actually, before that actually I have this question, which is these bounds, they probably change on form if you change bases, right? If you go like for
certainly, yeah.
Yeah.
So if instead of using the Warsaw basis, if I use a different basis,
Yeah, so
the bounds will change form.
yeah.
Change form like covariantly under a bit change.
Yeah.
Their physical content is the same.
Yes, but they probably, instead of being like strictly positive, they will be certain inside some range. Is that so? It's hard to tell that. Because
I don't think so,
yeah.
because
Yeah, I can't
physical
see
observables are, so observables don't really care about the basis we use for things, right? So like the fact that an operator is positive is a statement of, norm squareds of states, and it's requiring that cross section positive. So that's something that's true independent of what base we use. So if there's a clean positivity statement in one basis, it should turn into some positivity statement in another basis. It might look more complicated in one basis than another. It might involve messier sums of Wilson coefficients, but the statement should still remain.
Yes. What I wonder is, what I mean is that if we just at a different basis just lose the information about positivity, which means because the changing of bases, it's not necessarily it's linear, but not necessarily positive without coefficients, right? Like, for instance, if you go to what they call observable bases and so on. So that's
but it oh, well, I mean, it's not necessarily going to be that some Wilson coefficient is positive anymore. It might be that this Wilson coefficient is larger than this Wilson coefficient. No, it'll be positivity of sums of Wilson coefficients, and those themselves might not all be positive, but that's okay.
Exactly. Yes. Good,
yeah.
Good. Okay, so just the last one and short one. When you mentioned about the bounds on flavor violation, so you didn't have any assumption on that, like on the operators itself, like you didn't assume, for instance, minimal flavor violation and anything, right?
That's right.
Okay.
Yeah.
Okay, thank you. And I will.
Yeah, and I mentioned this, but it might have been too briefly. Our bounds neither demand nor forbid minimal flavor violation.
Mm-hmm. Okay.
Minimal flavor violation is sort of orthogonal to our bounds in that sense.
Thank you. I would highly appreciate if you can provide us your talk. Yeah.
Oh yeah. I'll send you the slides tomorrow.
Yes. Thank you. Thank you very much.
Or I'll send them to my host, I guess, and he can forward them to the group.
Absolutely. Yes. Thank you.
Okay. Any other question?
Hello. I'm just curious. So you were mainly talking about higher dimensional operators up to like 8, but we can basically construct a further higher dimensional operators by adding derivative or particles. Can this kind of bound be obtained for the arbitrary higher dimensional operators?
Oh, sure. Absolutely. Yeah. So if the number of, okay, so let me say this in momentum space because that'll be easier. So for operators whose forward amplitudes go like s squared, s to the 4th, s to the 6th, etc., are even powers of s, and the straightforward like vanilla dispersion relation applies, but you just divide by more powers of s to extract the pole, right? So for example, I had a paper some years ago where we were bounding the Remmen to the 4th operator in the EFT of gravity. So that goes like s to the 4th, right? Those are 8 derivative operators, and you could do the same thing with the standard model EFT. But for the operators that instead of going like s squared go like, so the dimension 6 operators go like s roughly, but for the operators that go like stu, or so momentum to the 6th, momentum to the 10th, etc., you would have to use some more exotic argument like what I had to use for dimension 6, but it absolutely can be done.
I see. And also this is somehow related, but if the higher dimensional operator involves like a gauge couplings, for instance, and which is kind of subject to the renormalization group evolution, and can we say that those kind of bound can be true for every scale during, in the course of the RG evolutions?
And in fact, this is a cool question because so suppose you force one of these positivity bounds at some energy scale in the IR, okay, where the EFT is true, and now you okay, what about this lower energy in the IR where the EFT is also true? Are the bounds still going to be true? And yes, and what this means is that analyticity and causality actually enforce particular constraints on the signs of beta functions. Oh, yes.
Sounds interesting.
And a whole lot of work done in that direction. Most people Wilson coefficients, but indeed, bounding the sign of beta functions is also something they can using these techniques.
I see. Thank you.
Okay, other question or comment? Okay, if not, then let's thank speaker again. Thank you very much.